Dirk, thank you so much for sparing time to come and talk to us about your solution that is going to help us extract fresh water from seawater. Our deployment is over salt pans. These are huge 1 acre facilities, many of them together, where billions of liters or gallons of seawater are evaporated using solar thermal to extract salt. Our effort here at Granted is to capture this moisture and put the greenhouse gas, which is H2O vapor, trap it and convert it back into pristine water, just like the hydrological cycle on Earth. So, let us start by understanding the superpowers of your solution, the greenhouse, the inflatable greenhouse that you have created using patented technology. So, Dirk, this is the first question that we want to ask from you. Tell us about the marine resilience of your greenhouse setup.
Sure. The structures that we build are a combination of composite material and inflatable material. So the two of those together come together in our patented material, which offers an incredible inflatable structure capable of really high loads, whether it's wind, snow, rain. Our inflatable structures can handle that. We use only a marine grade PVC reinforced inflatable materials. And those materials are about as good as you can get at resistance to the marine environment.
Traditionally, the greenhouses suffer from material yellowing and brittleness in high heat zones. Tell us about the UV and heat degradation redundancy properties that your setup, the inflatable greenhouses, may have.
So the structural component of our materials has a very high heat distortion temperature. It's in excess of 200 C. And the marine grade PVC materials that we use are also very heat resistant. They'll go north of 100 C very easily. And the two of them together, they're thermally fused. So there is no adhesive used to put them together. So they can operate well north of 50 degrees C without a problem. We then cover the structure with it's a reinforced poly PVC, which has about as high a UV protection in a plasticized product that you can expect. And in really solar climates, say in the desert, you can expect about 4 to 5 years, but we always make those so they're very easily replaced.
Definitely. Doug, what we understand is when we are installing uh, inflatable structures floating over our saltwater ponds to extract water, these structures may run to a length of 100 meters, forming tunnels. Do you think your structures will be able to take the PSI of air within these structures? And are there any functions to avoid buckling of these structures since they are inflated?
Well, without doing some on the ground testing, I can't really speak to it except to say that the structures are engineered for very high snow loads. So that's an externally applied structure, which would relate, I would think, directly to an internally applied vacuum in the structure. And, we can accept north of about 50 to 55 pounds per square foot of snow load. So that's in heavy wet snow, that's about 3 feet or a meter of really heavy wet snow. So I don't expect there would be a problem, but it would be good for us to do some testing just to make sure.
Definitely spoken like a true scientist. We need more data to establish how we can further strengthen these structures. From some of the demonstrations that I have seen, Dirk, of your product, I understand there are joints and beams that we can add to the structure to reinforce its tension from the roof above and from the sides also. Okay, moving on to the next question that we want to ask from you. This is about the dynamic wind loading. As you understand, we are not just in desert environment, we are in marine environment, places which are close to the sea and can experience winds up to 75 miles per hour. We understand traditional greenhouses come with tethering facilities. How does your greenhouse, which uses inflatable struts and pillars, deal with the coastal monsoon winds or active pressure areas?
Well, it does really well, Bhuvan. It's designed and with a finite engineering analysis to handle above 75 mile per hour wind loads. And with additional tensors, we can increase that above the 75 miles an hour. And in this particular application, I think we would have additional tensors that if you had the time to prepare before a storm, you could add those tensors, which would increase the resilience dramatically.
And another very interesting point, Doug, that you had also raised earlier was that in during high impact events such as cyclones and tornadoes, given that your structure is an inflatable structure, it can also be deflated if we get a heads-on caution. So that is also a great feature built into your structure for resilience purposes.
Yeah, our greenhouse, the key to it is that it can be erected in about a little over an hour for the structure itself. So that would lend itself really well to the structures that we're talking about here because they could easily be not necessarily deflated, but you could just take the modules apart and stack them all and secure them. You wouldn't even have to deflate it, but once you could take all these modules apart, it's kind of like it's a modular system with brackets that interface with saddles that are secured to the inflatable member. And there's little bolts, which in this case we would probably switch to some sort of an absolute marine resistant bolt, but those could be replaced and removed really simply, and then just stash them all like a pile of boards or something and secure them if there was a wind event coming.
Definitely. And Dirk, the Lego-like properties of your construction methodology are really interesting. Some of the demonstrations that we saw also came with blower fan installations, which will be critical for our operation because we are blowing exhaust air from the dehumidification unit across these tunnels to capture more moisture from the surface of salt pans. Tell us more about these facilities that you are in building for installing exhaust fans or blower fans within the structure.
Sure. You bring up a point that I need to address. So this is not a continuously inflatable structure. So this is more like the tires on your car where you pump them up and then they stay inflated. You don't need to continuously add inflation pressure like many inflatable structures. But to speak to your requirements with the flanges or the ducting, we have a similar situation in our greenhouse now where we attach a ventilation exhaust fan, which weighs about 10 pounds and it has a 10 by 10 inch interface. And so we take a triple wall polycarbonate that gets attached to the inflatable structure, and then that can be cut out to attach any sort of ductwork that you would want.
Fantastic, fantastic. Uh, uh, Doug, in an environment which is off grid, like our salt pans, which also has wind events happening, we are expecting there will be some punctures. Like you said, these structures act like tires. There may be some punctures. We are looking for solutions which are easy to repair, easy to mend if there are some incidents of puncturing or slashing of the external membranes. Does your solution also permit such repair work on at field on ground?
Yes, one of the reasons we chose the PVC was its resistance to UV and marine environments, but it's also very easy to repair with some solvent and two-part cement. You can patch PVC readily in the field and expect a very durable, lasting patch.
Fantastic. So, Dirk, we've already spoken about, how your system takes care of seam integrity, high pressure, both internal and external. Where we want to move on now is on order delivery and logistics for our partners to understand how resilient your operations are. So, tell us what are the biggest advantages of inflatables in terms of portability. One. Second, when we order 100-meter tunnel system, what is the stored footprint of that system? And can the entire structure be delivered on a standard flatbed truck and deployed without heavy cranes or specializing rigging?
Yeah, that one of the main benefits of inflatables is what they call their stowability. So it means it can be stowed in a much smaller volume than the structure would occupy when it's erected. And our ratio is, on the order of about 15 or even 20 to 1. So the volume of the structure versus the structure as it comes delivered. Our typical greenhouse comes in 5 small boxes that weigh about 30 pounds each. So that allows a customer to get those shipments via UPS or FedEx, and then it's delivered to their porch. They don't have to deal with a freight carrier and a lift gate on a truck. So it has that convenience certainly, and in these kind of scales, all that is replicated. So if you had 100-meter long greenhouse, the volume of the stowed good would be really much much smaller than other typical structures as they come, and yet it would go up in far faster time. It would be on the order of probably about, I would guess, 5 to 6 times easier to set up in just time, man hours than it would be to do a conventional poly hoop house structure.
Certainly, sounds like it is a very hands-on kit that you are preparing, no tool installation that you have developed. Tell us, going back to one of the earlier observations you had made, you mentioned your setup is a modular setup. And while we are talking about 100 meters or extensions of 200 meters or overlapping structures, tell us how does your setup make sure that the coupling systems do not allow for the air, the saturated air, the humid air to escape? What systems have you got in place to maintain those airtight seals between sections, modular sections?
So in this application, I think we would recommend that we build essentially a cap structure out of the reinforced poly material. And it's a 330 gram per meter squared material and has a reinforced poly fabric in there. I think we would devise a system that would be much easier to do than our greenhouse for these long tunnels. So we would probably divide the 100 meters long into probably 5 sections that would be basically like caps. So they would be all sealed except where they come to join, and we would do a Velcro joint there, which would seal the joints as well. So you'd probably have 5 separate caps to comprise a 100-meter long tunnel.